Turn the lights back on. Wow. Retro electro tech. When real audio ruled the world.
Greetings, all of you fine people dwelling in the land of vintage audio. This is Retro Ernest of Retro Electro Tech, and I decided to roll a part 2 video concerning this Pioneer SX828. Okay, so we are looking at this unit from a different viewpoint. We have our control board here. I pulled the main amp board. So I'd like to briefly recap on my initial findings after I safely powered this unit up. As I mentioned before, things were a bit staticky, crackly, with a few pops here and there. The relay also dropped out a few times, and all this happened briefly while I was exercising the controls. After that, the problem, it hasn't returned, like I said, at least yet. Now that said, I ran the receiver for a few hours here and there, injecting a test signal into the various outputs. I checked the tuner, and all is working okay. Not as good as it could be, but okay nonetheless. Could there be other problems that were contributors to the initial noise and relay dropout I just described? Of course, it's a 50-year-old stereo with what appears to be, the original components for the most part, except for some transistors that I could see were replaced, and I'll point those out when I get into some testing and all that. The point is, there may be something intermittent going on in this unit that is hiding from me at the moment, and may pop up again at some point, which is why intermittent problems can take some time to track down. Sometimes they're kind of a pain in the butt. There are things that can sort of help you along when you're in that diagnostic mode, exposing suspect components to temperature extremes, for example, like hit them with some freeze spray, put a little heat on them, see if you can get them to cross over that tipping point a little if they're already teetering on the edge. See if you can get them to produce noise or even downright fail, whatever. But those are some things you can do. I'm not going to get into that right now, no need. Another thing I want to bring up in this part 2 video is I was contacted by a viewer the first time around who pointed out the blue Sanyo caps here on the control board that have a bad rap within the world of electrolytics, just like those 2SA725 and 726 transistors I mentioned that have a bad rap in the world of semiconductors as well, especially as they age. And yes, the viewer is completely correct about these Sanyos. Of course, along with that, some batches, prove to be more problematic than other batches. And these have obviously been functioning in this unit without failure for 50 years. So I guess the big takeaway in this part of the video so far is that ideally, all of these electrolytics in this piece of equipment should go, regardless of what they are, whether we're talking about these problematic little blue Sanyos, these United Chemicons, there's these Alnas that are populating this piece of equipment, whatever the case, they're all old, and the way that they degrade, the way that they fail, they just need to go. So I've been in touch with the customer, and I have more of a feel as to what I'll be doing in here that's going to work within the budget, of course. So I'm going to be pulling all the electrolytics from the control main amp boards, get those 2 toasty caps replaced that are on that power supply board I pointed out in video 1, and get some transistors matched up to replace the ones I mentioned. So let's get into that. Okay, as you can see, the tone board is flipped around, and I'm going to start pulling caps off the board, do a little bit of light testing on them as opposed to in-depth testing. I'm just going to check the ESR, capacitance, and so forth. I'm not going to get too deep into it because I don't want to burn a lot of time doing that. So anyways, I'm going to start getting some of these caps out of here. Okay, y'all, so I'm getting caps removed from the board. I'm moving and a grooving in the right direction. Now let me zoom in on something real quick before I move on. Hopefully I'm not zoomed in too close to where things are getting blurry. I don't think so. Now, as I've been going along physically removing the capacitors from their positions, I've been noting the polarity of the cap before I pull it out versus the screen printing you can see here. You see the little positive symbols I'm sure you can, hopefully. Well, this is the negative side of the cap, the positive side of the cap. So I've been noting, you know, the polarity, and everything is looking good. So far, so good. There are cases where the screen printing is incorrect. You know, they made a boo-boo, and you know, if you do run across discrepancies like that, you're going to want to investigate further against the schematic, and you know, use more than one source of information to make sure that everything is in fact correct, or if it was just an error in the screen printing, so forth and so on. So be aware, don't take the screen printing on the board as gospel, and that's of course if there is any. So you need to be in charge of that before you go yanking out components. Note the polarity of electrolytics. Note the pinout of transistors, you know, emitter, base collector, whatever the case. So that's all. So let's go ahead and move on. Like I said, I'm going to get the rest of these caps out on the control board here, the amp board. As you can see, the electrolytics have been removed from the control board and from the main amp board. And what I wanted to touch on just briefly is some information that might prove helpful to some of the newer players, and that is, when I was going through and desoldering, I was just removing caps, you know, all at the same time and setting them off to the side so I can test them. Now, sometimes I will do that, but sometimes I'll just remove a component and replace it, remove a component and replace it. So that way, you know, you don't lose track of where the various components that you're replacing go. In this case, I have, you know, service data. I have this reference here, this board layout that shows the physical location of the various components and their values. So when I go, you know, in reverse and, you know, reverse navigate, I'm not sitting there scratching my head because some time has gone by and I've forgotten where this goes, where that goes. So you either want to have a reference like that, something that you have available via the service data, or create a reference. You know, you can draw a rough sketch and just list where the various components go and their values. You know, you don't have to be an artiste. Or, you know, in this day and age of camera phones, snap an image, although I recommend that you print the image and draw some lines from the components you're going to be replacing, write their values in. So again, you don't have any issues with you know, figuring out where things go. Not a big deal, nothing real groundbreaking there. Now you can get to that destination via the schematic, however, that's unnecessary eye strain and brain strain, examining a schematic and, you know, translating all of the, you know, component interconnections versus the physical layout of the board. Those are two different animals. So anyways, I just wanted to bring that up, so there you go. Okay, and here we are zoomed in to the display of our LCR meter. Now this is going to be a topic that is difficult to condense so that I'm able to keep this portion short, or the whole video for that matter, and still be able to convey the information I want to convey, give you sort of the nuts and bolts of what I need to give you so that you'll understand more or less what's going on. And I recommend that you do your homework on this topic as far as loss tangent, dissipation factor, or tan delta, ESR, because again, this is a topic that's very, very big, and you can go down all kinds of different rabbit trails. So again, just do your homework, and I'll try to convey as much information as I can. Okay, so let's start by talking about the existence of that non-existent perfect capacitor that possesses zero losses. A lot of you know that a capacitor is reactive, and pure reactance from a pure perfect capacitor wouldn't dissipate energy and would fully absorb and release power without loss or energy dissipation. We know that's not the case with resistive elements. Okay, they dissipate energy, and the byproduct of that dissipation is heat, so there is loss. So the inherent losses in a real-world cap stem mostly from dielectric resistivity. So the dielectric is opposing changes in voltage, and as such is dissipating energy. So there's that resistive aspect going on, And we also need to consider, other losses aside from inherent losses that stem from, degradation, age. In this case, we're pulling really old caps out of an old receiver. So I wanted to bring up that point as well. So with our LCR meter here, especially what you're looking at here, this measurement up top here, the 0.061, is our dissipation factor, and that's a measurement that is quantifying those internal losses in a real world imperfect cap. Okay, and I'll talk a little bit more about how that's happening, a little bit more behind the scenes there. So for lack of a better description, I suppose, we have this manifestation of the losses that I referred to a moment ago being shown here via this dissipation factor measurement, or tan delta. And if we think back to the perfect capacitor, this phase angle here that we're looking at is a representation of that pure and perfect capacitor. So if we consider the capacitor's reactive behavior and the fact that voltage lags current leads voltage, then we have this 90-degree phase angle here that we're measuring against to quantify those losses once again. Anyways, let's go ahead and move forward. So moving forward here, we're looking at this phi angle or phi angle. Some say phi, some say phi, 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 pho, phum, whatever, tomato, tomato. Or shall I say, we're measuring from this impedance or resistive plane here, and the negative JXC, or this reactive axis here, and we see our loss angle in this area here, or tan delta. So with the ability to be able to measure these angles, our tan delta, our loss tangent, to be able to work things out the way the LCR meter does, we can get a bigger picture look into the health of a capacitor. It's a nice tool to have. It has its limitations. Once again, I'm not going to get into that, but what I want to say real quick before kind of closing out this section is I do have a cap hooked up to this meter, obviously, a 3.3 mic, 25 volt, solid aluminum electrolytic, one of those CSSA type caps, these blue Sanyo caps that a viewer commented about, and I was aware of their reputation, but I do appreciate this gentleman chiming in. Not all batches are as bad as some. It's kind of funny how that works. Some batches are really bad, some not so much. But in regard to this particular cap, this 3.3 mic cap with an M class tolerance rating of plus minus 30%, you can see we're right up against that upper edge, which we don't know how close this cap sat to that originally as far as its capacitance reading, because I have no way of knowing what the excuse me, original reading of this cap was when it was fresh and new. And as far as our dissipation factor here, this 0.061, well, sometimes when we don't have data, we have to sort of use experience and or compare against similar caps, similar series of caps, and of course caps in the same range, so we can kind of extrapolate from there, in other words. So anyways, the dissipation factor looks actually good, because I was able to come across some old Pioneer data that was showing a tan delta table for this type of cap, CSS cap, solid aluminum electrolytic cap, and it was showing right about 0.1 or 0.2 tan delta measurement, and that was a generalization, of course, but we're below that at 120 hertz, and if we bump this up, all of these values change with frequency. That's something else that, I could get into, but I'm not going to get into too much of that. And, just, in regard to capacitive reactance and frequency and doing different tests at different frequencies and so forth. I mean, yeah, it's something that, again, look it up, study up on it, but at 1 kilohertz here, we're at 0.252. So, again, that's looking pretty fair. And also too, let's go back to 120 hertz and I'll show you what the ESR is looking like at 120 hertz. And let me switch gears here. So 20.9 ohms at 120 hertz with these low value caps at lower frequencies. It's not uncommon to see these higher ESR readings, okay? And if we were to check it against other caps, even newer caps, we would see at 120 hertz, we'd see higher ESR readings as well. Now, is that to say that this cap is in good health? Not necessarily. I mean, it's probably pushing against its limits. And I haven't even checked leakage current, which I'm not going to do anyways. We know about, resistive models, series resistance that looks more at our ESR and our parallel resistance that looks at our leakage current and the problems, leakage current can cause with producing noise and distortion, disrupting bias, and, DC getting onto areas that we don't want DC getting onto, such as, with coupling capacitors and vacuum tube gear. We know that, when we have leaky coupling caps and we have DC getting onto the grids of output tubes, we can overdrive those output tubes and red plate those tubes and so forth. So we know about all these problems, and I'm not saying that this cap is necessarily in good health, because it could be leaky, and more than likely most of these electrolytics in here are probably more leaky than anything else, okay, as far as ESR versus leakage. So my plan was just to pull them out anyways, and that's exactly what I'm doing. So I just wanted to talk on this a little bit, but you'll see as I keep increasing frequency, look at the ESR there. If I go up 1 kilohertz, then look at 10.8 on the ESR, 10 kilohertz, 7 ohms, and so forth. 100 kilohertz, 3 ohms. So, there's things you need to consider again with frequency, and that's the last thing I'm going to say before closing this out is, again, knowing what we know about the behavior of electrolytic capacitors, capacitive reactance, and so forth. We want to be sure that these caps are going to be able to function properly when subjected to the various frequencies of various circuits. And again, you have to use the right cap for the right job. So that's really all I want to say about this, because this kind of stuff can go on and on forever. So let me go ahead, and what I'm going to do now is I'm not going to get really into putting more caps on the tester. I think that this was kind of a good place to start with, getting you guys thinking, and those of you that already know this stuff, great, but to get some of you newer cats thinking about the behind the scenes aspect of what's going on with caps and how we obtain these different measurements and all that. So let me go ahead and move on. I'm going to get these transistors out. I haven't got those out yet, but I'm going to get those out and start checking them. I'm curious about their leakage and their gain characteristics, and I want to match up the replacement transistors in terms of gain and all that. So let me go ahead and get to it. Okay, so I have the transistors laid out that I pulled from the control board, and here's a schematic here. These are my replacements, the KSA 992s, and these are the ones I'm removing, of course, the 2SA 725s that are known to have issues. They're on the poop list with many other transistors that start exhibiting problems with age. But let me zoom in closer to the schematic, and I will show you which transistors I'm replacing. So hopefully you can see these FET compound pairs here. Okay, so these BJTs here, these NPNs, 2SA725s that make up this FET compound amplifier pair here. That's what I'm going to pull from here. Now, of course, I've matched up the gain, and I've looked at the specs and what have you. And it's not so much in this situation that you have to match things with aerospace precision, but you do want to match things appropriately, of course. And let me go ahead, and I'm actually going to bring in some data here just to show you what the gain is of the 2SA725s. And let me just go ahead and do that for starters. And here I have my trusty Japanese transistor manual. I'm glad I have these old books. I'm turning Japanese, I really think so. But anyways, I was looking up some information on the net, first off, for these 2SA725s, because I wanted to compare what the data sheet had to say versus the HFE of these actual transistors that I pulled out, because I did a quick preliminary with this little tester here. And anyways, the information that I obtained on the net, because there wasn't a lot of information on the 725, there's all these websites. When you do a search like 2SA 725 data sheet, PDF and all that, and you start looking around, there's all these sites that indicate that they have that information available, but when you go in, it's like trying to navigate the open ocean, and there's all kinds of crap and ads and this and that. So I just give up on that stuff. But there was one website that it wasn't showing a data sheet, but it was showing the specs and all that, and the HFE didn't jive to the HFE of these transistors that I pulled off the control board. So in my trusty Japanese transistor manual here, if I go ahead and let me scoot this just a hair, and I'm going to zoom in, and pardon my camera, sometimes it makes funny little creaky noises and all that stuff when I zoom in. So whatever, it's not my bones creaking. So I don't know if you can see this very well. But right here is where we want to be. These are the HFE listings for both the 2SA725 and 726. You can see 500. And so let's go ahead and compare our HFE for the transistors I pulled versus the KSA992s that are going to be replacing these. Let's just kind of go in and match up these transistors and make sure everything jives okay. Okay, so I have on the tester here, I'm just going to zoom in just for kicks, not that it's all that important, and I really doubt if you're going to be able to see it anyways. It's probably going to, yeah, it's going to blur. Let me see if it focuses for whatever reason. I'm not going to spend a lot of time on it. Yeah, to heck with it. But anyways, this is one of the 2SA725s that I pulled from the control board. And let me go ahead, it's a PNP of course, and let me just tweak around with the calibration knob-a-majiggy here. All right, so that's looking good, and we're on times 10 because I'm expecting an HFE in the ballpark of what I looked up in the Japanese transistor manual. So, and okay, I'm looking directly over the tester, and it might be hard to tell, but the needle is directly over 50 times 10 that, so we're at a HFE of 500. Okay, so just like the Japanese transistor manual indicated, it's actually right on the money. So now I'm going to do a quick leakage test, collector to emitter, and we are down there at 0, as we would expect from a good BJT here. And now collector to base, and right down there at 0. So, okay, so I have my other two SX828 hooked up. Let me switch it over to PNP. Tweak the calibration knob just a hair. Okay, and let me go ahead and I'm hovering right over the tester, and that needle is right on 50, so 50 times 10. So again, we have our HFE of 500. Let's do a quick leakage test. I'm expecting it to bottom out there. So it's looking good and looking good. Okay, now I want to compare with the replacements, the KSA992s, so let's do that. Okay, so let me get this clipped on a little bit better there. Here's our first replacement, our KSA992. Let me go ahead and click it on over to PNP, tweak our calibration just a hair. Looking good. And bada boom, bada bing, we're right over our 500 HFE. So we're nicely matched, okay? So let's check our second KSA992. And of course, I know that the leakage is going to be fine, but just for the sake of repetition, I suppose. Yeah, we're looking good. Okay. Okay, and here's our other KSA992. One thing I want to mention, the pinout between these and the ones I pulled are reversed, so when I go to install these, I need to flip them around 180 degrees. You know, these are emitter collector base, the others are base collector emitter, so you have to be aware of that. Always check your pinout. Okay, so let me go ahead and turn this on here and tweak the calibration. Actually, we're right on with the calibration. Let me go ahead and wouldn't you know, 500 on the HFE. Everything matches up just right between the two pairs of transistors, the replacements versus the oldies. So that's good. And for sake of consistency, there we go. Nice leakage. Nice leakage, meaning absolutely minimal, doesn't register on the needle, so we're looking good. All right, so here's what I'm going to do. I'm not gonna do the rest on camera as far as the that differential pair, the you know, the two pairs, that differential pair or long tail pair, two SA726s. It's the same thing. I'm going to pull them. I'm going to, you know, check their gain characteristics versus the gain characteristics of the replacements, and then just get them installed. So again, you know, we don't have to use critical aerospace precision matching. You know, I have one of those leader curve tracers that you sync up to your scope and all that if I wanted to get a bit more precise about matching up these transistors and so forth. But most of the time I just use my, especially for this gear here, this, you know, this old stereo gear and all that, and these old amps, this little transistor tester, man, it really does good in most cases. Again, like everything, you have to know its limitations. And the thing is that these two sync up really well. If I was to take these same transistors here, and let me just go ahead and do that just for kicks. Let me hook up, before I close this out, let me just hook up one of these new ones. They're going to be pretty close. You know, they'll be a hair off, but, you know, which is to be expected between different testers, but you'll get the point. Okay. 514 on the HFE. So man, you know what? That's looking good. I've done many comparisons between these two different testers, and yeah, they jive well together. And anyway, so what I'm going to do, like I said, I have the rest of the caps on order that I don't have in stock. When those get here, I'm going to start repopulating the boards. I'm going to have these transistors in. Like I said, I'm going to go through, touch up some solder joints, clean things up a little bit, clean up that tuning condenser, stuff like that, just little stuff here and there. You know, when I get everything back in, then I'm going to go ahead and roll some footage for a quick part 3 video, you know, do some testing and all that, and I'm sure that things should be fine. Of course, you never know until you do the final testing, but everything's looking good. I'm speccing everything out really nicely for this receiver and for these replacements. Otherwise, yeah, I'm expecting things to look a lot better once I'm done. So anyways, I'll be back with the final half. So, you know, like I always say, guys, peace, love, music, and the vintage audio that brings it to your ears. Till next time, you all take care.
This is a poor man's shoe production.